Good morning. In this section, we will introduce the notion of a proof and describe methods for constructing proofs. A proof is a valid argument that establishes the truth of a mathematical statement. A proof can use the hypothesis of a theorem, if any, axioms assumed to be true, and previously proven theorems. Using these ingredients and the rules of inference, the final step of the proof establishes the truth of the statement being proved. Formal proofs of theorems designed for human consumption, assuming mathematicians are human, are almost always informal proofs, where more than one rule of inference may be used in each step, where steps may be skipped, where axioms being assumed and rules of inferences are not explicitly stated. The reason elementary steps are omitted in a proof is the limitation of a human mind. Almost no one can hold 200 pages of detail in one's mind. This fact defines the mathematician's definition of elegant. An elegant proof is short but complete within the confines of omitting elementary steps. Here is some terminology. A theorem is a statement that can be shown to be true. In mathematical writing, the term theorem is usually reserved for a statement that is considered at least somewhat important. Proposition, a less important theorem. Proof, a method for demonstrating that a theorem is true. Fact, a synonym for theorem. Result, a synonym for theorem. Axiom is a statement assumed to be true and for which no exceptions have been found. Postulate, synonym for axiom. Lemma, a less important theorem that is helpful in the proof of other results. Corollary, a theorem that can be established from a theorem that has been proved. Conjecture, a statement that is being proposed to be true, usually on the basis of some partial evidence, a heuristic argument, or the intuition of an expert. Understanding how theorems are stated. Example 0. Complete the statement below by adding the qualification. If x is greater than y, where x and y are positive real numbers, then x squared is greater than y squared. Solution. The foregoing statement really means for all positive real numbers x and y, if x is greater than y, then x squared is greater than y squared. Stated symbolically, we have for all x, for all y, p of x implies q of x, where p of x is x greater than y and q of x is x squared greater than y squared. And the domain of discourse is x and y are elements of the reals and x and y are greater than 0. Methods of proving theorems. The objective is to prove a theorem of the form for all x, p of x implies q of x. Show p of c implies q of c. C is an arbitrary element of the domain. Apply universal generalization. Direct proofs. In the statement, p implies q. P is assumed to be true. Axioms, definitions, and previously proven theorems are used with rules of inference to show that q must also be true. Definition 1. The integer n is even if there exists an integer k such that n is equal to 2k, and n is odd if there exists an integer k such that n is equal to 2k plus 1. Note that an integer is either even or odd, and no integer is both even and odd. Example 1. Give a direct proof of the theorem. If n is an odd integer, then n squared is odd. Solution. The theorem states for all n, p of n implies q of n, where p of n means that n is an odd integer and q of n is n squared is an odd integer. Assume n is an arbitrarily chosen odd integer. P of n is true. Then we can state n as n equal 2k plus 1, where k is some integer. N squared is equal to the quantity 2k plus 1 squared, which we eventually fact out to 2 times the quantity 2k squared plus 2k, which plus 1, and then we let the amount in the between the parentheses 2k squared plus 2k be an arbitrary integer L, and then we form n squared is equal to 2l plus 1. 2l plus 1 is an odd integer by the definition, and so is n squared. N squared. Give a direct proof that if m and n are both perfect squares, then the product of m and n is also a perfect square. An integer a is a perfect square if there is an integer b such that a is equal to b squared. Solution. To produce a direct proof of this theorem, we assume that the hypothesis of this conditional statement is true. Namely, we assume that m and n are both perfect squares. By the definition of a perfect square, it follows that there are integers s and t such that m is equal to s squared and n is equal to t squared. The goal of the proof is to show that the product mn must also be a perfect square, where m and n are m is equal to s squared and n is equal to t squared together. This shows that the product mn is equal to s squared times t squared, which implies mn is equal to the quantity st squared, using commutativity and associativity of multiplication. By the definition of a perfect square, it follows that mn must be a perfect square, because it is the square of st, which is an integer. We have proved that if m and n are both perfect squares, then mn is also a perfect square. Proof by contraposition, called indirect proofs, called proof by contraposition. The essence of a contrapositional proof is that P implies Q is equivalent to not Q implies not P. Example 3. Prove that if n is an integer and 3n plus 2 is odd, then n is odd. Assume n is even. N is equal to 2k by the definition of even. 3 times 2k plus 2 is equal to 6k plus 2, which is equal to 2 times 3k plus 1. 3n plus 2 must be even because if n is even, we have found that 3n plus 2 is a multiple of 2, namely 2 times 3k plus 1. Since an integer cannot both be even and odd at the same time, 3n plus 2 is not odd. However, the statement 3n plus 2 is not odd contradicts the hypothesis that 3n plus 2 is even. Therefore, n must be odd. We have proved the theorem if 3n plus 2 is odd, then n is odd. Proof by contradiction. It is also called an indirect proof. Because the proposition R and not R is a contradiction wherever R is a proposition, we can prove that P is true if we can show that not P implies R and not R is true for some proposition. Proofs of this type are called proofs by contradiction. Example 9. Show that at least 4 of any 22 days must fall on the same day of the week. Let P be the proposition, at least 4 of 22 days fall on the same day of the week. This means that at most 3 of the 22 days fall on the same day of the week. Because there are 7 days of the week, this implies that at most 21 days could have been chosen. And for each of these days of the week, at most 3 of the chosen days could fall on that day. This contradicts the premise that we have 22 days under consideration. That is, if R is the statement that we have 22 days, that 22 days are chosen, then we have shown that not P implies R and not R. Consequently, we know that P is true. Prove that the square root of 2 is irrational by giving a proof by contradiction. Let P be the proposition, the square root of 2 is irrational. Not P is the proposition, the square root of 2 is rational. Assume not P is true. If the square root of 2 is rational, then there exist integers a and b with the square root of 2 is equal to a over b, where b is not equal to z, and a and b have no common factors, so that the fraction a divided by b is in lowest terms. R is the proposition that a and b have no common factors. By squaring both sides equally, we obtain 2 is equal to a squared over b squared. Hence, 2b squared is equal to a squared. By the definition of an even integer, a squared is even because it contains a factor of 2. Since a squared is even, a must be even also. Since a is even, we can write a is equal to 2c for some integer c. Recall that 2b squared equal a squared, and substitute 2c for a, arriving at the equation 2b squared is equal to 4c squared. We have now shown that the assumption of the square of not p leads to the equation the square root of 2 is equal to a over b, where a and b have no common factors, but both a and b are even. That is, 2 divides both a and b. Note that the statement the square root of 2 divides is equal to a over b, where a over b have no common factors, means in particular that 2 does not divide both a and b. Because our assumption of not p leads to a contradiction that 2 divides both a and b and 2 does not divide both a and b, not p must be false. That is the statement, the square root of 2 is irrational, is true. We have proved the square root of 2 is irrational. Now we explain some exercises that are similar to the ones that are assigned for this section in our text. 1. Use a direct proof to show that the sum of two odd integers is even. 1. Let a be an arbitrary odd integer. That's a premise. Let b be an arbitrary odd integer. That's a premise. Let a equal 2s plus 1, where s is an arbitrary odd integer. We do this by the definition of odd integer, and we do the same for b is equal to 2t plus 1. And in step 5, we have the sum of a and b is 2s plus 1 plus 2t plus 1. And then we use the distributive law of multiplication over addition to find that a plus b is equal to 2 times s plus t plus 1. And then we let u is equal to s plus t plus 1, the sum of two arbitrary integers, and 1. U is an integer. And we find that a plus b is equal to 2u by substitution, and the sum a plus b is even by the definition of an even integer. 17. Prove that if n is an integer and n cubed plus 5 is odd, then n is even using a proof by contraposition. Solution. A proof by contraposition. Let P be the proposition that n cubed plus 5 is an odd integer. Let the proposition Q be n is an even integer. We must show that the contrapositive, that is, not Q implies not P. We must show that if n is odd, then n cubed plus 5 is even. Let n equal 2k plus 1, where k is an arbitrary integer. N is an odd integer. We go ahead and perform the computation, and what we find is that n cubed plus 5 is equal to 2 times the quantity 4k cubed plus 6k squared plus 3k plus 3. We let u be the quantity in the parenthesis, 4k cubed plus 6k squared plus 3k plus 3, an arbitrary integer, and we have now shown that n cubed plus 5 is equal to 2u, an even integer. N cubed plus 5 is not P. We have shown the contrapositive that not Q implies not P. Now, a proof by contradiction. Let P be the proposition that n is odd. N squared is odd. The product of two integers is odd. N cubed is odd. The product of two odd integers is odd. We subtract n cubed plus 5 from n cubed, arriving at 5. And 5 is even. The difference of two odd numbers, in particular n cubed plus 5 and n cubed, is even. This is a contradiction. The integer 5 cannot be even and odd simultaneously, hence not P and n is even. 23. Show that at least 10 of any 64 days chosen must fall on the same day of the week. We give a proof by contradiction. If there were 9 of of fewer days of each week, of each day of the week, this would account for our 63 days. But we chose 64